In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 67. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with challenges and prospects to ensure optimal operation of transformer. Transformer is a large electromagnetic device for converting power between two voltages, and its working principle is based on the theory of electromagnetic induction and mutual induction. The low and high voltage windings that are wound from insulated conductors onto a magnetic core made of laminated sheet steel, Sergio material, cold rolled grain oriented material, which has made to enhance the flux linkages. Total assembly would then be enclosed in a steel tank, normally filled with transformer oil. Most of the power transformers would have the higher efficiency, and it is of the order 95% to 99%. For large power transformers with very low losses, the efficiency can be as high as 99.7%. The power loss, though it is of a small percentage, but that appears as an amount of heat which is very large in absolute terms. As because this amount of heat would have been turned out to be the most critical factor in determining the maximum power at which a given unit may be safely and economically operated. There are several factors that are causing transformers to run hotter. A. Abnormal increase of ambient temperature. B. Operation at significantly higher loads. C. Internal obstructions to oil circulation system due to blockage in the heat dissipation channels or radiator tubes. Problem in the cooling cycle. Poor contact of tap changer due to insufficient contact pressure or having higher contact resistance as developed. Short circuit between turns of winding coils. Short circuit between iron core silicon steel sheets, that is laminated sheets. Operation of transformer at significantly higher loads refers mainly due to have some external reason, and if there would have been a severe overload, then the respective copper loss must therefore be increased, leading to an increase in transformer temperature. Short circuit between turns of winding coils that would have to occur due to insulation failure. The circulation of short circuit current that leads to generate an exuberant heat, causing a massive temperature rise of the affected transformer, and sometimes it is so severe that the transformer winding part might have been burnt out. If the insulation between silicon steel sheets that would have been damaged as due to usual aging or some internal vibrations in between the laminations, core laminations rather, then there must have a flow of eddy currents causing an occurrence of local overheating, which ultimately leads the iron core to overheat. It is obvious that during operation, if the heat is generated in transformer and its heat dissipation cycle would continuously be in a balanced state, then all through the temperature of its associated components should have to be in stabilized condition. However, under the same state of conditions, if the oil temperature would have shown higher than usual by more than 10 degrees centigrade or the load remains unchanged, but the temperature continues to rise, then it is quite evident that some fault there would have been developed inside the transformer. The hottest spot winding temperature that would actually be the most crucial factor in determining the life of the transformer. The hottest spot copper temperature is thus to be determined by the sum of the temperature of the cooling medium, the average temperature rise of the copper, and the hottest spot allowance. The hottest spot allowance at rated load would thereby 10 degrees centigrade for transformers as designed with 55 degrees centigrade average winding temperature rise by resistance, whereas that allowance would be of 15 degrees centigrade for transformers designed with 65 degrees centigrade average winding temperature rise by resistance. But it is important to note that of a given capacity, a transformer, while designed to operate with 65 degrees centigrade average winding temperature rise by resistance, would usually have to undergo higher amount of losses than that of a similar transformer designed to operate with a 55 degrees centigrade average winding temperature rise by resistance. Combination of cellulose based insulation and mineral oil would thus to form an inseparable insulation system in a transformer. Any rise of operating temperature from 55 degrees centigrade or 65 degrees centigrade that would have an effect on the overall mechanical, chemical, and electrical properties of the oil cellulose insulation system. To enforce a normal life expectancy, it is very much necessary to impose thermally upgraded cellulose-based paper as for the insulation while designing with 65 degrees centigrade average winding temperature rise by resistance. Thermal upgradation of cellulose-based paper has usually been carried out by applying some chemically modified processes to reduce the rate at which the paper decomposes. Kraft paper is the most commonly used insulation paper whose thermal resistance is only up to 105 degrees centigrade. However, thermal upgradation can be made possible by the usual process of ethylation or cellulose acetylation reactions, that is ethanolation, or by the addition of stabilizing agents such as urea, melanin, and dicyanamide, which contains two cyanide groups bound to a central nitrogen anion. Cyanoethylation is a process for the attachment of CH2CH2CN group to another organic substrate. Acetylation is a chemical reaction that introduces an acetyl functional group into a chemical compound, and that involves in replacing the hydrogen atom of a hydroxyl group with an acetyl group, that is CH3CO. Thermally upgraded kraft paper would able to withstand an operating temperature of up to 120 degrees centigrade. That is, the average winding temperature rise would remain 65 degrees centigrade. To enhance the operational properties to enhance the operational properties of transformer insulation dynamics that may have to reveal the reasons behind the rise in component costs as well. The chemically modified processes that should have to be done as of the precise recommendation of ANSI or IEEE C57.100 2011. Sustainable temperature rise in liquid field transformers. All electrical and electromagnetic devices, even at their normal operation, would have to produce some heat. Accordingly, in case of transformer, also there would have been an internal temperature to rise even at its normal loading operation. So far, the transformer nameplate rating as mentioned is rather be the average temperature increase of windings above ambient. So far, the transformer nameplate rating as mentioned is rather be the average temperature increase of its windings above ambient. However, designed ratings are typically based on a maximum ambient temperature of 40 degrees centigrade. Any sort of abnormal rise in temperature that would have the potential to shorten the transformer's lifespan, which must have a direct relation with the criteria of insulation system as provided. Transformer temperature rise that involves on the resultant effect of heat generation and distinct modes of heat dissipation cycle to its surrounding environment through a constant transferring process of conduction, convection, and radiation. Any imbalance due to hindrance in between heat generation and heat dissipation criteria, then temperature rise of the transformer that would have been the most indicative parameter to justify its true operational efficiency. In response to the design criteria of temperature and temperature rise, it is quite evident that the selection of insulation materials as used for conductors and wires in transformers should thus to be well assigned by the corresponding temperature class of insulation. Insulating materials, as they are mainly concerned with electric current, short circuits, and incidence of overheating, so they are to be categorized with different temperature ratings. Temperature ratings are based on the classes of insulation YA, EB, FHC that associated with different types of materials with having different physical and chemical properties. Classes of insulation based on the types of the materials would have been differentiated mainly with their respective thermal stability. Thermal stability of a material is rather to be characterized with its ability to resist deformation at a certain temperature. Therefore, thermal stability of an insulating material can thus be determined by its ability to counter the thermal stress without causing any sort of degradation of its usual mechanical properties like strength, toughness, or elasticity at a given temperature. However, conventional designs based on mineral oil and cellulose insulation are being normally incorporated as main insulation for power transformers. But transformer's lifespan is invariably determined by the resistive ability of its designed insulation system to withstand most major short circuit current forces. Insulation system, if designed with high temperature withstanding materials, then that would allow to construct transformer of a given capacity significantly more compact in size as well as best extent of life expectancy. IEEE C57.154 2012 standard provides specific requirements and guidance in designing, testing, application of the transformers incorporating with high temperature insulation systems of using a hybrid combination of high temperature and conventional insulations. Temperature limits for class of electrical insulating materials. Insulation class Y, maximum temperature withstanding ability is 90 degrees centigrade, 194 degree Fahrenheit, and in Kelvin scale 363.15. Plain cellulose paper, types of materials, silk, cotton, certain thermoplastics that might have been softened above 90 degrees centigrade. A 105 degrees centigrade, 221 degree Fahrenheit, 378.15 degree Kelvin. Types of material: reinforced silk, cotton, cellulose paper, impregnated with varnish or insulation oil. E. Maximum withstanding ability, temperature withstanding ability 120 degrees centigrade, 248 degree Fahrenheit, 393.15 degree Kelvin. That is powder plastics, polyurethane, molded polyvinyl epoxy resins, polyethylene terephthalate, B. 130 degrees centigrade, maximum withstanding ability, 266 degree Fahrenheit and 403.15 degree Kelvin. Inorganic materials such as asbestos, glass fibers, mica with varnish. F. 155 degrees centigrade, maximum withstanding temperature withstanding ability, 311 degree Fahrenheit, 428.15 degree Kelvin. Mica class B materials that perform well at higher temperatures. H. Maximum temperature withstanding ability 180 degrees centigrade, 356 degree Fahrenheit, 453.15 Kelvin. That is fiberglass, mica, asbestos impregnated with silicon rubber. C. 220 degrees centigrade, 428 degree Fahrenheit and 493.15 degree Kelvin. Maximum temperature withstanding ability. Polyimide flames, quartz, mica, Teflon, polyimide, enamel. Relative thermal endurance index in degree centigrade as per insulation class. Insulation class Y, 90 degree maximum hotspot temperature that are to be allowed 90 degrees centigrade, that is relative thermal endurance index is less than 90 to 105 degrees centigrade. A 105 degrees centigrade maximum hotspot temperature allowed, that is relative thermal endurance index less than 105 to 120, whereas E 120 degrees, that is less than 120 to 130. B 130 degrees centigrade less than 130 to 155. F 155 degrees centigrade maximum hotspot temperature that are to be allowed, and relative thermal endurance index is less than 155 degrees centigrade to 180 degrees centigrade. H maximum hotspot temperature allowed is 180 degrees centigrade, relative thermal endurance index less than 180 to 200. And C maximum hotspot temperature allowed 220 degrees centigrade and relative thermal endurance index is 220 to 250 degrees centigrade. Now, maximum hotspot temperature, which must be equal to rated ambient temperature of the equipment, often it is designed with 40 degrees centigrade plus a temperature rise plus a 10 degrees centigrade hotspot allowance. Winding hotspot temperature refers to the specific area within a transformer that has the highest temperature. Electrical equipment would usually be designed with an average temperature below the rated hotspot temperature to allow for acceptable life. Insulation, though, would not suddenly fail while being reached at the hotspot temperature, but its usual operating life would have to decline rapidly. As of a thumb rule, its life would have become half for every 10 degrees centigrade temperature rise. Most important to note. Concerning issues as regard to life expectancy of power transformer. Power transformer's loading capability would have been limited mainly by its winding temperature. However, the temperature of the winding is not being uniform throughout, and the load limiting factor is actually related with the hottest section of the winding, commonly called winding hotspot. And this winding hotspot area is located somewhere toward the top of the transformer. Increased temperature is the real concern for a transformer as because that adversely affects the insulating properties of its crucial internal components. Dielectric integrity is a key factor in long-term reliability of a power transformer. And once this has been affected, that has posed challenges in comprehending the deterioration of total insulation system within core type power transformers. Dielectric integrity of the power transformer's insulation system is directly related with the behavior of insulation material placed at the surroundings of the winding conductors, typically known as kraft paper, which undergoes accelerated degradation at elevated temperatures. The cellulosic insulation has the characteristics that include dielectric breakdown strength, impulse strength, energy dissipation factor, shrinkage, tensile strength, and air resistance capacities. All these characteristics should have to depend on temperature. As because with temperature and time, the cellulose insulation that has to undergo a process of depolymerization, depolymerization, depolymerization process that would cause to lower the cellulose chain length, and that affects its mechanical strength, which results in the brittleness of insulation. As the cellulose chain gets shorter, the mechanical properties of cellulosic paper, such as tensile strength and elasticity, would have been degraded. However, over the time, those cellulosic paper would have become brittle and not at all capable of withstanding short circuit forces. Such type of consequence would therefore characterize the end of life of the solid insulation. Cellulose made solid insulation is sometimes showing more than 2% water content, and that incur an additional risk when operating at high temperature. Because of higher operating temperature, the residual water as trapped in cellulose made solid insulation may reach in bubbling conditions and has to escape under the form of water vapor bubbles. Consequently, these bubbles may then move with the oil flow or get trapped in the winding, causing degradation of both cellulosic paper and oil insulation system of the affected transformer. as the cellulosic paper is typically sensitive to temperature. So, necessary online monitoring system that should be incorporated to have an early detection of the winding hotspot temperature with the best mean available. Transformer insulation, that is paper and oil, and a paper oil combination rather. That acts as of the again I repeat. Transformation, sorry, transformer insulation system, that is paper and oil, that acts as of the crucial supportive structure such as winding, interturns, separate different components from each other and from the core and tank. Aging of cellulose insulation, that would have been a permanent breaking of hydrogen and covalent bonds between cellulose polymer chains under collective impact of moisture, oxygen, and heat during continuous operation of transformers. For the period of continuous operation with certain level of complexity, it is also to be understood that the insulation system is more often sensitive to electrical, thermal, chemical, and mechanical stresses, which are obviously responsible for damaging its dielectric integrity. Fiber optic temperature sensors would have been specifically designed for systematic real-time tracking of winding hotspot temperature in high voltage transformer, both oil field and dry type. Fiber optic temperature sensor probe is embedded in a standard spacer and then made to insert between the successive layers of disk windings. High capacity based transformers are normally built with circular disk windings as because such windings would have the most preferred characteristics to handle higher short circuit forces and phenomenon of larger voltage impulse. As the temperature probe consists of solid state sensitive element bonded to an optical fiber, so it is specifically designed which must have to comply with ASTM D2413 and D149 standards. It is what mentioned that to design dielectric system for any of the electrical equipment, it is very much crucial to select the material by judging its two main properties such as dissipation factor and relative permittivity. ASTM 1711-22 is the standard terminology relating to electrical insulation, where it is intended that the dielectric loss index of a dielectric system is the product of its relative permittivity and its dissipation factor. The dielectric loss index is also thereby proportional to the energy loss converted to heat, which in turn would have the loss of efficiency of electrical equipment. Let's stop here. Further to be continued at later stage. Thank you. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.